Hello everyone, welcome to this session. In the last session, we talked about the loss function of the model training, right? So in this section, we will talk about the optimization techniques. Let's use a linear regression model as an example. So in this case, mean squared error, MSE, is a mostly widely used loss function for this. So we can see the function is here, get the average of the difference of the actual value and the predicted value to the power of 2, right? So now we will write this function, substitute the value of the yj predicted inside this equation. So we can see the loss function becomes what? Yj minus a multiply xj minus b. So a and x, they are vectors, right? So we can see this function is a loss function of the linear regression model using mean squared error. Now we need to minimize this function, right? Yeah. So this function is an unconstrained optimization problem, and we can see we can describe it as here. So a and b are the decision variables to be optimized, and we want to find the ultimate value of these ones, right? So, and also this method is a continuously differentiable and convex. So we know there's only one optimum. This is the local optimum, and it's also the global optimum, and it's also continuously differentiable, right, using the calculus knowledge. So one method that is fit for this optimization is a gradient descent algorithm, right? So this is a traditional mathematical optimization algorithm that is fit for this kind of problems. So you may ask me that why we don't use AI-based optimization techniques, why we don't use GA or don't use PSO here. So the answer is that normally the training costs a long time. So the traditional optimization techniques can be faster, right? So if we use GA or PSO and with a large data set, the training time could be very long, right? So now let's have a look at the gradient descent method. So gradient descent method is an iterative optimization method. So we go through the iteration by iteration to gradually improve the value of the x that we want to optimize. And it aims to find a local optima of a differentiable function. Yeah. So we can see it like that. Xk plus 1, the k plus 1 iteration x equals to the k iteration x minus alpha k, and this one we call it the gradient of the loss function. So we can see it one by one. Alpha k, we call it the step size, and alpha k must be the larger than 0. In machine learning, we call it a learning rate. So this one, we read it as a gradient of the loss function L at the point of xk. So this has several information in it, right? So if we write it in detail, this is the partial differential, the partial derivatives of the loss function L with respect to each of the variables x1k and x2 xnk, right? It's a partial derivative of this one. So we call it the gradient. So this one, the k is the number of the current iteration, and n is the dimension of x. So this is the gradient of the L at xk. So now we see that how the gradient descent algorithm works, right? So first we set x0 to be any starting point. Then we iteratively use the previous equation, for equation 1, until the k plus 1 and xk, these two, the loss function, the difference is very little. We call it eta, right? So this is, we want to for example, we can see the gradient descent algorithm to optimize this function, Lx1, x2. We can see we randomly start here, and this gradient provide me the direction. So this is the step size. Step by step, I arrived at the optimal point here. This can also can be seen from the counter of the L from here, right? So this is the gradient descent algorithm. So this is for optimizing the objective function or optimizing the loss function to do minimization, and this is based on the partial derivatives, right? So this is a loss function, the gradient descent. So if you don't have much knowledge in calculus, you just understand this is a traditional mathematical optimization algorithm that can optimize the loss function, and that is good enough. Okay, thank you very much. Bye-bye.